Industrial processes typically generate vast amounts of surplus heat which is lost to the ambient. Instead of releasing the surplus heat to the surroundings, this energy can be recovered and utilized, for example, for local district heating. Efficient management of the heat exchanger network is an important factor in maximizing the surplus heat recovery. This is accomplished by adjusting the flow of cold stream through the heat exchangers as the amount of heat generated by the different heat sources vary over time. This paper considers the problem of optimizing surplus heat recovery from an industrial cluster using a parallel heat exchanger network. Traditional real-time optimization typically requires detailed process models, production schedules, and real-time process measurements in order to optimize the process. However, in an eco-industrial park with multiple heat sources operated by different companies, sharing of local production data and models may not always be desirable. We therefore consider a model-free method where the heat recovery is maximized using only a single temperature measurement measured at the end of the heat recovery network. This avoids the need for temperature measurements from the different heat sources. The model-free nature also implies that the proposed method is not susceptible to plant-model mismatch and thus can be used irrespective of the type of heat exchanger, the number of heat exchangers in each split stream, heat exchanger fouling, etc. Since we have multiple inputs and a single output, we use a multivariable extremum seeking scheme in this paper. We show that fast Fourier transform-based gradient estimation scheme provides a natural and an intuitive framework for multi-input single-output systems, such as the heat recovery network studied in this paper. Fast Fourier transform allows us to decompose any time-varying signal into the different frequencies that make it up. Using this idea, we add a small sinusoidal perturbation to each input with a unique perturbation frequency and use fast Fourier transform to isolate the effect of each perturbation frequency on the end temperature measurement. This directly provides the gradient information with respect to each input. Optimal operation can then be achieved by driving the estimated gradients to zero using integral action. By mapping the time series data into a series of frequencies, we show that fast Fourier transform allows us to easily extract the effect of different input perturbations from the single temperature measurement and use it to optimize surplus heat recovery from an industrial cluster.